Hey everybody. Today what we're going to be talking about is the normal distribution. So when it comes to the normal distribution, what it starts with is data and statistics. When we look at any set of data, you may find that when you go to create a histogram with it or any type of, bar graph, there's of course data that will skew to the left, there's data that will skew to the right, and then there's some that are just kind of all over the place. When we're talking about a normal distribution, what that means is that when you create a histogram with this data, it starts to look something like this, where there's just this one peak and then it goes back down. And there's this real symmetrical sort of look to the data. That's what is called a normal distribution. What you may have heard of this being called is the bell curve. There's a lot of different things in our daily life that kind of follow a natural bell curve. For example, gotta think of something, but like the heights. So heights of people. So when we look at the height of people, if we were to have a whole bunch of people, we measured everybody's height and had all of the data there, what we would notice is that it starts to have this one peak and then it kind of tapers off. Most people are right in the middle. We have some people that are very, very tall and then some who are very, very short, but most people are kind of right in the middle. Then there's a whole bunch of other things too, like in machinery, when we are going to, fill up any like a pop can or any type of machinery that you would have in a factory tends to follow a normal distribution. Blood pressure, exams, even when I give out exams a lot of the time, most students are kind of within a certain range. And then there's, of course, those people that are kind of at the very, very top and some of that are at the very, very bottom, but most people are kind of in this middle ground. And that could be represented by a normal distribution. And what I want to show you guys is just a really good example of kind of where we can see the normal distribution occurring. So what I'm going to do is hit start on this. So here's kind of what we have is we have a few rows with balls falling through. And what we notice is that probability wise, most of them are going to actually land right in the middle. This should look like a game that you've seen before. If you've ever watched The Price is Right, this looks like Plinko. So if you ever actually wanted to win Plinko, the best prize is actually right in the middle. So statistically speaking, you should be dropping your Plinko chip right above that. And what will end up happening is that you're going to have the highest chance of winning that prize if you drop it right above that point. So as I keep talking, what we're noticing here, most of those balls are falling somewhere in the middle. We have a few outliers. Some are on the very far left, some on the very far right, but for the most part, they're going right in the middle. This is what I'm talking about with a normal distribution. What we notice right in the middle, we have the highest bar. That's going to be our mean or our average. 50% of our data is going to be to the left of that, and 50% of our data is going to be to the right. I could keep this going, and it would just actually create a better and better bell curve. But what we can see right now is it's already pretty good. Okay, I'm just going to stop that. So that is the normal distribution known as the bell curve. This is how a lot of university classes are actually scored. There's a lot of things in our daily life that follow a normal distribution. Kind of getting into the mathematics of this, getting a little bit diving deeper into it. Let's get started. All right, so what I wanted to keep talking about, just again to kind of go over some definitions here. When someone talks about the normal curve, what they're talking about is a symmetrical curve that represents the normal distribution. And the normal distribution is what I was talking about already. You may also hear this being referred to as a bell curve. So the normal distribution is data that results in a unimodal symmetric distribution about the mean. Unimodal, all we're saying there when we talk about unimodal is that it's data that has only one maximum. And I mentioned that earlier. Here's what we notice that data look like is that we can kind of take all of those bars that we notice were being created and we can create what's called a bell curve where we have this point right in the middle. Right in the middle is going to be our mean. Depending on what course you're at, you may be representing mean with the Greek letter mu, or you may be using x with a bar over top to represent the mean. So what we've noticed is that when we have data that can be represented by a bell curve or by a normal distribution, what has been found is that 68% of data falls within one standard deviation of the mean. What has also been noticed is that 95% of data falls within two standard deviations. And lastly, 99.7% of data falls within three standard deviations. How this looks on a bell curve, how we can actually break this down a little bit more. What this is saying is that the 68% rule is that 68% of my data is going to fall within one standard deviation. So one standard deviation to the left and one standard deviation to the right. So if 68% of my data is represented in this portion of the bell curve, what I can say is that if I split this evenly, that 34% would go here and 34% of my data would go there. For the next part of the rule, it says that 95% of my data falls within 2 standard deviations of the mean. So 2 standard deviations to the left, 2 standard deviations to the right. What I already know is that 68% of my data is already in the middle. So if I subtract 95 from 68, what I'm left with is 27%. But that 27% would have to be distributed evenly between these two bars. So when I divide it by 2, I get 13.5%. Next, what we can look at is the 99.7. So what was found is that 99.7% of data falls within 3 standard deviations. So again, 3 to the left, 3 to the right of the mean. We already have 95% of my data calculated. So I'm going to take 99.7 and subtract off 95. What that leaves me with is 4.8%. So this bar here and this bar over here have to add up to 4.7%. I'm going to divide by 2 because it has to be even, and this gives me 2.35%. We have a little bit left over. 99.7% of data isn't quite 100%. So we have these 2 sections on the outside here and here. That's going to be where the leftover bits are. So we're going to go 100%. I'm going to take away 99.7, and I'm left with 0.3. Like everything else, I have to divide that by 2 because I have to evenly distribute that. So 0.15% and 0.15% is what is left over. This is what the 68, 95, 97.7% rule tells us, and this is how we can break up a bell curve or a normal distribution into a bunch of sections. The 68, 95, 97.7% rule allows us to break a bell curve or a normal distribution into a bunch of pieces. Let's take a look at an example. Okay, here's an example. Male polar bears on average weigh 525 kilograms with a standard deviation of 58 kilograms. Draw a normal distribution representing this data and answer the following questions. Okay, when we go to draw any normal distribution, what goes right in the center is our mean. What we've been told is that our average or our mean is 525. So I'm going to put 525 kilograms as my mean. What I've been also told is that my standard deviation is 58. Along the bottom of the bell curve, what we notice is that we have the mean right in the middle, and then to the right, we have 1 standard deviation, 2, and then 3. What we're going to do to include the data that we've been given is I'm going to start with the mean, and I'm going to add 58, and that's going to tell me 1 standard deviation above the mean. So what I get there is 583 kilograms. I'm going to add 58 again. And that's going to tell me the weight of 2 standard deviations above the mean. We'll do it one more time, and that will give me 3 standard deviations, like so. I'm going to do the same thing going to the left. However, instead of adding 58, I'm going to take away 58. So what we get first is 467 kilograms. From there, I'm going to subtract 58 again to get 409. And one more time to get 351. What you may notice is that a lot of people will write the number that I wrote below above the bell curve. If that's the way it's written, that's totally fine. Mathematically speaking, it really doesn't matter where these are. What I'm going to include now is the percentages that we had just talked about from our previous bell curve. I'm going to throw those in right now. Okay, so these percentages have now been added in. What we can now do is use the data that we have, in this case, talking about the average weight of polar bears and the standard deviation, and we can place that with the normal distribution. This is going to allow us to solve a bunch of questions relating to this scenario. So let's take a look at the questions below. What we will get there is 16%. All right, lighter than 409 kilograms. Just like before, where does 409 fall on my normal distribution? Well, that's right here. If a polar bear is lighter than that, it needs to be less than 409 kilograms. So it needs to be to the left of this value. So we're going to add up 2.35% and 0.15%. What we will get there is 2.5%. Okay, last one. We're going to look at what is the percentage of polar bears that would weigh between 351 and 525. Just like before, I need to identify where on the normal distribution does this happen. Well, we're looking between 351, which is right here, and 525, which is right here. If I need to add in between all of these, I need to add all of these three percentages together. So we'll have 34% plus 13.5% plus 2.35%. And we're going to add that all up. What we get here as an answer is 49.85%. Of course, what we could have also done to calculate this is we could have taken 50%, which is the left side of the bell curve, and just subtracted off 0.15%. What we've done here is super useful. We're able to use the normal distribution to answer a question about something that would follow a bell curve. Where this is a very limited skill is that what if I wanted to know what percentage of polar bears weigh more than 550 kilograms? Well, 550 falls right in the middle here. It's somewhere in between here. And if I wanted to know how many polar bears are heavier than this, well, then now I need to know what percentage is heavier than this value. Why right now we're unable to solve this is I don't know where that falls in between 0 and 1 standard deviation. It doesn't really help me. Right now, it's great if I know exactly +1 standard deviation or -2 standard deviations. But honestly, for the most part, this isn't really realistic. It's very, very rare that we would be looking at that specific of a value. What about everything in between? This is where Z-scores are going to come into play and going to help us. If you need help with Z-scores, please watch the next video. If you need help with anything in this video, please let me know. Thanks.